Those don't always follow the lectures, but at the beginning, of course, they're pretty close. Later on, they're like. I'm probably going to lecture on some different variations of the course, so later on there'll be some things that are different. Okay, the last time at the end of the hour, we were in the process of examining this question about the possibility of degeneracies. I'll remind you that in the Stern-Gerlach experiments, there was no evidence on the basis of measurements of spin that the Hilbert space had any more than 2 dimensions. And so we just assumed, for the sake of simplicity, that it had exactly 2 dimensions, so that each of the eigenspaces of the various components of magnetic moment were one-dimensional. Now the question is that, and I promised we'd come back and examine the question of degeneracies later. So that's what we're doing now. The question we want to ask is that if there were degeneracies, how would we know? This is not a mathematical question, it's one of physics. It has to start from the postulates of quantum mechanics. So to answer this question, I'd like to examine a somewhat idealized experimental situation in which we imagine that we've got some pure state, initial pure state psi 0. We make a measurement of an observable A, and we throw away all the outcomes except A sub n. Then, according to the postulates of quantum mechanics, after this measurement, the state of the system, which I'm calling psi 1, is given by the projection operator, which projects onto the nth eigenstate of the observable A. That's what I mean by PAN. Acting on psi 0 gives me the new state psi 1. We then take this psi 1 state and we feed it into a second measurement of a different observable B, which also has a bunch of outcomes, but we throw them all away except for one of them we call B sub m. And again, according to the postulates of quantum mechanics, the state that emerges after the measurement of B sub m with the eigenvalue Lorca. After the measurement of B with the eigenvalue B sub m is given by the projection operator onto the eigenspace of the operator B with eigenvalue B m acting on psi 1. That's the state psi 2. Okay, that's just following the postulates. Now, let's ask for the probability that we measure first AN and then secondly B sub m in a sequence of experiments, a sequence of measurements like this. This is a product probability. It first need to multiply the probability of measuring AN in the first place by the postulates of quantum mechanics. It's given by taking the input state psi 0 here and sandwiching it around the projection operator PAN, and then dividing by the norm of psi 0, square norm of psi 0. That's the probability of getting the AN. And then we need to multiply by the conditional probability of getting B sub m, given that we had AN in the first place. And that probability is again by the postulates of quantum mechanics, given by taking the input state psi 1, sandwiching it around this projection operator P sub d m, and dividing by the norm of psi 1. So this is the compound probability. Now, let's take this denominator psi 1 here, and let's plug in this expression for psi 1 in terms of this projector. Gives us, in terms of PA0, PAN acting on psi 0. If I take this as a bra, I turn it around and I get a PAN dagger. So this is the same thing as psi 0, P sub AN dagger times P sub AN times psi 0. That denominator. However, projection operators have emission, so I can drop the dagger if I want the left-hand factor. And projection operators are idempotent too. That means their square is equal to the operator itself. So we get the square of PAN in here, but it can just be replaced by a single copy of PAN, like that. And if we do this, then we see that this denominator, psi 1 cancels with the numerator up above. Now likewise, this numerator that has psi 1's in here, we can substitute in and express it in terms of psi 0s using, again, this expression. And so if I copy this down, I get to clean it up and copy it down, I get the probability of these two successive measurements giving two given successive outcomes as being equal to the state psi 0 sandwiched around a product of three projection operators, PBM, it's PAN, PBM, PAN, psi 0, divided by the square norm psi 0, the normalization. like that. That's what we get. All right. Now, suppose we perform the experiments in the reverse order, doing the A first, the B first, and measuring B sub m, and then A second, and measuring A sub n. And let's write down what the probability is for doing that in a reverse order. The formula is just the same as the one above, except we swap the A's and the B's and the N's and the M's. So it's psi 0, P, D, M, P, A, N, P, B sub m, psi 0 divided by norm squared psi 0, like this. Now the question is, are these probabilities equal? Do we get the same answer? And the answer is no, because in general these projection operators, the A and the B projection operators, don't commute with one another. So the triple product of the first expression and the one of the second expression are the same. This is something that is one of the surprising aspects of quantum mechanics. In a sense, it's a saying that the measurement of one of these observables mixes up the statistics of the other one. We saw this already in measurements of magnetic moment. If we measure the mu x first, it affects the outcome of the subsequent mu z measurement, changes the statistics of the mu z's. Likewise here, doing this in one order or the other makes a difference because measuring one observable affects the statistical outcome of the measurement of the second observable. Now, on the other hand, there are circumstances in which these two probabilities are equal. They're equal in particular if the operators, A and B, the two observables, commute with one another. This is because if the observables commute, it implies that their projection operators commute. PAN and PDM commute. This follows because projection operators are actually functions of the original operators themselves, and functions of commuting operators are commuting. So in the present case, it means, for example, in this enumerator up above, I can take the PDM and move it to the right of the PA, whereupon we get a PAN squared, and that's just PA because it's idempotent. So you get the product PAN times PBM in the upper expression. Likewise, in the lower expression, I can take this PBM and move it to the right of the PA, and then you get a PB squared, which is the same as the without the square. So again, you get the same product here. You can write this in either order, of course, because they commute. But the point is that the two expressions now become equal. So we can say that these probabilities are equal if the operators commute, A and B. And this is a consequence, as I just explained, of the measurement postulates of quantum mechanics. All right. Now, there's a converse of this as well. By the way, the mu x and mu z, for example, in the Stern-Gerlach experiments, certainly don't commute, and so these probabilities are not equal for that kind of experiment. But they do commute when we have equal probabilities. Now, there's a converse of this as well, which is that if the measurements of the probability, if the measurements, compound measurements of subsequent measurements of two observables like this are equal for all choices of the eigenvalues, A, N, and Dm, and also for all choices of the initial state psi 0, then one can show that the operators commute. So it's really an if and only if. Is a necessary and sufficient condition for the equality of these probabilities is the commutativity of the operators. This is what this means, amongst other things, is that the commutativity of operators has experimental consequences, and in fact it can be determined in principle, it can be determined experimentally. Not that anyone actually does this, because it would be very difficult to do these in full completeness, but the point is that it's in principle an experimental matter to decide whether operators commute. Remember here in the postulates of quantum mechanics, we're trying to build up the mathematics from the physics. We're not starting with a mathematical problem, which is what you've mostly done up to this point in your study of quantum mechanics, but rather starting with physics. All right. So that's the meaning of commuting operators. Now, let's go back to the question about the possible degeneracies. This is related to how do we know the dimensionality of the Hilbert space when we're starting with the postulates of quantum mechanics and building up the Hilbert space. How do we know, for example, those twofold, in the case of the spin operators or magnetic moments, We decompose the Hilbert space into two subspaces. How do we know that those subspaces are really only one-dimensional? Well, the answer on something like this is that this state psi 1 lies in the eigenspace A n of the operator A, according to the postulates of quantum mechanics. Now, if the operators A and B commute, it then follows that the projection operators for operator B, there's more than one of them here. I'm just listing one of them for the single outcome, but there's other outcomes here. There's a whole series of projection operators. It turns out that those B projectors leave this A eigenspace invariant. So they take any vector in that eigenspace, such as this psi 1, and they map it into another vector in the same eigenspace. So what that means is the states that come out of all of these different B outcomes are still eigenstates of A with the same eigenvalue. That hasn't been changed. This is if they commute, as I'm assuming here. On the other hand, the B values are different. So what that means is we got a collection of states, and what they now lie in are simultaneous eigenspaces of both A and B. And if there's more than one of these, and if the B values are different, and if the states don't vanish, then these different states have to be orthogonal to one another because the B values are distinct. And so what we've got now is a collection of orthogonal vectors that lie inside this eigenspace of AN, which therefore must be multidimensional. As we say, what we've done is we've resolved the degeneracies of the A operator by applying the B operator. And in fact, what we've discovered is simultaneous eigenspace by using commuting operators. We've discovered simultaneous eigenspaces. This is clearly related to this theorem we discussed earlier about commuting operators possessing simultaneous eigenbasis. All right. Now, once we've got these in, the simultaneous eigenspaces, how do we know that those are maybe degenerate? Maybe they're multidimensional. How do we know? Physically, how do we know? Well, the answer is we search for further observables that commute with both A and B, and remember, in principle, that's an experimental matter to decide that, to see whether these measurements of the further observables will cause any further resolutions of these degeneracies. And if we can't define any such operator, then what we say is we've reached the end of the game. These resulting simultaneous eigenspaces are one-dimensional, and we have what we call a complete set of commuting observables. Complete set of commuting observables means that the simultaneous eigenspaces of all the observables taken together are one-dimensional. And so if you just choose normalized vectors in each of those spaces, you get an eigenbasis for the whole Hilbert space. This is what you do, for example, in hydrogen, where you have these NLM states like this. The first one is the eigen quantum number of Hamiltonian, the second one is the operator L squared, and the third one is LZ. If you just talk about the Hamiltonian itself, it's degenerate. But the list taken together gives you a basis, a non-degenerate basis in this space. A question in principle in this procedure is, how do you know if you've gone far enough? Maybe you can't find any observables that produce any more resolution, but maybe you didn't look hard enough. Maybe they're actually there. The answer is to that question is that in principle you really don't know that you've gone far enough. What you do if you stop at a certain point is you're restricting yourself to a certain kind of physics. Here's an example of this. Frequently, as I'm sure you know, in discussing quantum mechanics of an electron, we frequently treat the electron as if it's spinless. We do this for simplicity in introductory courses, but we're just writing a psi of r or something, and never mind the spin component. Well, what this amounts to is using the position variables as a complete set of commuting observables, but ignoring the spin variables. It's physically justifiable to do that if the spin variables are not important for the physics you're interested in. In fact, this happens frequently in practice because spin only interacts with magnetic fields and not with electric fields. So if you have electrons that are moving in electrostatic fields and they're non-relativistic, low velocity, then it often happens that the spin is not important. And you can, in effect, you can deliberately stop in your search for a complete set of commuting observables before you've taken into account all the degrees of freedom of the system, that even if you know about them, because maybe you don't care about that physics. All right, there's many examples of this. Later on, if you add this extra physics, then what you'll find is that what you were previously speaking of as non-degenerate spaces like this one actually become degenerate. Because, for example, you need to say you need to put in an extra quantum number that tells you the spin quantum number. This is a resolution of the previously what you thought as non-degenerate eigenspaces. Now it's actually twofold degenerate. The magnetic quantum number of spin tells you which one you're talking about. Okay. So this is the story of the dimensionality of the Hilbert space and what to do about degeneracies. All right. Now, here's another important point, which is that I didn't write out the postulates of quantum mechanics once again today because I didn't get here in time. But as you'll recall, the predictions of quantum mechanics refer to probabilities. That is, they are of a statistical nature. By the postulates of quantum mechanics as I presented them, quantum mechanics makes predictions about the probabilities of various outcomes and measurements. These probabilities are measured in practice by taking an ensemble of identically prepared systems and subjecting them to the same measurement and then making statistical accounting of the results. Quantum mechanics doesn't tell you anything about what happens to an individual system. In the orthodox interpretation of quantum mechanics only makes statistical predictions. So, for example, if we go back to the Stern-Gerlach apparatus, so where we first measured mu x, and then we sent a plus beam in to a measurement of mu z, and then we got two outcomes. This one we threw away. We've got two outcomes here, plus and minus, and each one has a 50% probability. This is the tandem Stern-Gerlach experiment. Now, quantum mechanics tells you these probabilities. You can calculate them. But if you have an individual silver atom coming down this beam, quantum mechanics is not going to tell you, and it's polarized in the x direction with plus, that's given. Quantum mechanics is not going to tell you whether it's going to go up or down in the next magnet. It makes no statements about that. So it doesn't tell you about individual systems. So in the orthodox interpretation of quantum mechanics, it's probably safest to regard the wave function, later on we'll talk about the density operator, as representing not an individual system, but rather an ensemble of identically prepared systems. Although we oftentimes use this language such as the wave function of the electron, what the wave function is really describing is the statistics of measurements on an ensemble of electron systems which are prepared to be in the same state, such as this state here coming out of this first measurement. All right. Now, this is a way. If you keep this in mind, it's a way of avoiding many of the apparent paradoxes of quantum mechanics. All right. Now, some people don't like this, and they want to believe that quantum mechanics is not statistical, and the reason it isn't. The reason we think it is, but it really isn't, is because there are extra variables that we haven't measured, so-called hidden variables. And this leads into the subject of hidden variable theories, which I make some mention of in the notes. You can read about them. And you may also want to read the section in Sakurai's book on Bell's theorem, which deals with the same subject. Maybe if we have time later in the semester, we'll come back to some of those issues. But right now, I'm just giving you the orthodox interpretation of quantum mechanics. As long as I'm talking about statistics, let me make a few remarks, simple remarks. I think you know about this already. If we're doing ordinary, if we have an observable A and we measure certain eigenvalues A n, then the probabilities, let's call them Fn, are given by taking the state in question, assuming to be a pure state, and sandwiching it around the projection operator onto the corresponding eigenspace. This is from the postulates. If we were doing ordinary statistics and we had certain outcomes with certain probabilities, we'd compute the average of the outcome as being just the weighted sum of the probabilities times the values. It's just definition of the mean in statistics. However, in quantum mechanics, this mean value can also be expressed in terms of Hilbert space operations, and it turns out to be the operator A sandwiched around the state size sandwiched around the operator A, like this, as I'm sure you well know. Similarly, in statistics, we can define a mean square deviation or dispersion, which is the same thing as the sum on n of Fn times A n squared minus the square of the mean. That's the meaning in statistics. And it turns out this can also be written in terms of Hilbert space operations. It's as we say, the expectation value of the operator A squared minus the expectation value of the operator itself, quantity squared. This could also be written in another way. It can be written as psi sandwiched around an operator A1 squared, where the operator A1 is equal to the operator A minus its average value. This is the definition of A1. And again, this is straightforward to prove this, and I'm sure you've seen it before, so I won't go through it. But it connects statistics with Hilbert space expectation values. This first expectation value is oftentimes just abbreviated this way, leaving out the psi. If we do, then the angular brackets has kind of a double meaning. It's first of all a statistical average, but it's also an expectation value in the sense of Hilbert space operations. And likewise, this is a similar thing here. This could be written as just a squared without the size. If you use this notation, then some state psi is understood in writing this down. All right. Now, so that's all simple stuff that I think you know. Let me say something now that carries on with this idea of statistics. I'd like to address the question of the generalized uncertainty relations. The situation is the following. Let's suppose we've got two observables A and B, which don't necessarily commute. I'll put the result first. It says that the dispersion in A squared times the dispersion in B squared, the product of the two variances in a statistical sense, is greater than or equal to the quantity which is one quarter of the absolute value of the expectation value of the commutator of A with B. Quantity squared. That's the identity. So now allow me to prove this. The delta A squared is the same thing as psi sandwiched around the operator A1 squared, as I've indicated up here, where A1 is the difference between A and its mean value. Let me write this as just A1 times A1 acting on psi, like this. A1 squared, writing it out like that. These are observables, so they're Hermitian, so allow me to put a dagger on the one on the left, which is okay. Let me also define a ket alpha, which I'll define to be A1 acting on the ket psi. So that if I do this, this becomes the same thing as the scalar product of alpha with itself. Similarly, we'll say for B, we'll say that this is psi sandwiched around B1 squared psi, which is the same thing as the scalar product of beta with beta, where beta ket is the same thing as, or is defined to be B1 acting on psi, like this. And so the left-hand side of the theorem which I want to prove here is the same thing as alpha alpha times beta beta. It's a product of the two squares of these two vectors. Now, by the Schwarz inequality, this is greater than or equal to the absolute value of the scalar product of alpha with beta squared. So let's take a look at the scalar product of alpha with beta. What is that equal to? Well, it's the same thing as psi sandwiched around the product of operators A1, B1. And I'm using these relations here. Now, to make a little digression, if I have two operators x and y, I can write them this way as 1/2 xy minus yx plus 1/2 xy plus yx, an obvious identity. And that's the same thing as 1/2 of the commutator of x with y plus 1/2 of the anti-commutator of x with y. Where I'm using curly brackets for the anti-commutator, it's the same as the commutator except that it's a plus sign in it. Now, if x and y are Hermitian, then the commutator is actually anti-Hermitian, as you can easily show, whereas the anti-commutator is Hermitian. So, in this case, A1 and B1 are both Hermitian operators, and I can write this, therefore, as 1/2 the average value of the commutator of A1 with B1, plus 1/2 the average value of the anti-commutator of A1 with B1. Now, since the commutator is anti-Hermitian, its expectation value is purely imaginary. And since the anti-commutator is Hermitian, its expectation value is purely real. And so this scalar product over here, which is a complex number, is decomposed into the sum of the real and imaginary numbers, which must be the real and imaginary parts. And therefore, the absolute value squared at the left-hand side, which is what appears in the Schwartz inequality, is the sum of the squares of these two terms. And so therefore, it's greater than or equal to the sum of the square of just one of the terms separately, which is this first term here. It's greater or equal to 1/4 the square of the commutator of A1 with B1, expectation value squared like this. It would be equal to it if the anti-commutator vanished. Well, you see, this is almost the result we need, except there's just ones here instead of the operators without the ones. That's easy to take care of because the difference between the ones and the lack of ones is given up here. It's just the average value, which is an ordinary number, which therefore commutes with everything. So it drops out of this commutator, and I just drop the ones here. I'll use my fingers, and that proves the inequality. Well, so this is the generalized version of the uncertainty relations, and it puts limits on the possibilities of the dispersions for measurements of two operators. To be clear about the measurement of physical situation that lies behind this formula, I'm not talking about making successive measurements of two different observables like I was a minute ago when we measured A first and then B second and then swapped the order. This is a different situation here. We're talking about taking a single ensemble and then measuring the A's on it, and then taking the same ensemble and measuring the B's on it. Imagine this is a beam. We're going to put the beam through two different measurements, an A measurement and then a B measurement. That's what this refers to. This is the kind of thing you'd like to do. For example, if you wanted to make your beam as localized as possible in space and also as localized as possible, let's say, in the direction in which the beam goes. This is an application of the uncertainty principle because there's limits on what you can do by minimizing those two quantities. The most famous example of this is where we let A be the position and B be the momentum of a particle, let's say, in one dimension. And if we take the square roots of this, then what you get is, of course, then the commutator x with p is equal to my h bar. So if you take the square root, you get delta x delta p is greater than h bar over 2, which is the famous Heisenberg uncertainty relations. All right. Now, I'd like now to return to a Stern-Gerlach apparatus to make another point. In the original Stern-Gerlach apparatus, they used a beam of silver atoms. It was obtained by taking silver and heating it to a high temperature in an oven. You make a small hole in the oven so the atoms come out. You run it through a collimator to make a narrow beam. And this gives us what I'll call a thermal beam because it comes out of the oven. And then this goes into the way we described before with the measurement of some observable. Let's make the x component the spin now instead of magnetic moment. It's really the same thing. And there's two outcomes, the plus and the minus. Let's say we throw away the minus. And as I've explained in the basis of the postulates of quantum mechanics and the assumption that the Hilbert space is two-dimensional, we know that the system is described by a state vector, which is normalized. We'll assume it's normalized. It's some eigenvector lying inside this one-dimensional eigenspace where s of x equals plus h bar over 2. H bar over 2 instead of mu naught because it's spin instead of magnetic moment. All right, so the point is that the beam that emerges from the second apparatus is described by a definite state vector. Well, definite to within a normalization of the phase. The question then arises is, what about the beam that came out of the oven? Is it described by a state vector? In other words, what's the wave function? What's the spin wave function of the beam coming from the oven? Indeed, does it even have one? Well, the answer is it does not have a wave function. And here's how we can know this. We know this because if we take this thermal beam and we make measurements of all three components of spin, I'll call this S vector here, but that means Sx, Sy, and Sz. And by an average, what I mean is just what you do experimentally. You just measure the results and weight them by the number of atoms that came out one way or another. For example, in the X component here, this is what this thing does. It gives you 50% on either side, and since the answer is plus and minus h bar over 2, the weighted average is 0. So Sx averages to 0. The same thing is true for Sy and S sub z. So the result of the thermal beam is that the average of the spin vector is 0. As we say, the thermal beam is not polarized. The reason for that is that it's thermal. There's nothing in the oven to pick out any preferred direction, and because of thermal fluctuations and random collisions and so on, the average spin vector is 0. It can't point in any direction. Now, on the other hand, if the thermal beam were described by some state, let's call it chi, it would necessarily be possible to express that state as a linear combination of the z eigenstates, which we're calling S of z eigenstates, which we're calling plus and minus, with coefficients, let's call them alpha and beta complex numbers. If we assume that chi is normalized, then these coefficients satisfy the normalization condition 1. This comes from chi is equal to 1. We can assume the state is normalized here without loss of generality. So, my point is, to go back to the point, is that if, let's suppose the thermal beam were described by some definite state vector, if it were, we could do this expansion. And now we'll just calculate what the components, the expectation value of spin is, using the Pauli matrices, which we derived already in our previous exercise, so we know what those are. And if you go through the algebra of this, what you find is the answer is h bar over 2, and then what the Pauli matrices give you for the x component is twice the real part of alpha star beta. And the imaginary part, for the y component, it's twice the imaginary part of alpha star beta. And for the z component, it's the absolute value of alpha squared minus the absolute value of beta squared. That's what you get if you do the algebra. Now, it turns out that this thing is actually a unit vector. As you find by showing that n hat dotted into itself is equal to 1, that's some algebra to do that, and it ultimately boils down to the normalization. And again, I'll let you do that as an exercise. But let me just write this, therefore, as h bar over 2 times the unit vector n hat. And so what we see is that if the state of the beam is described by a state vector, then it necessarily is polarized in some direction n hat. But since the beam that comes from the oven is not polarized, it cannot be described by a state vector. So if you ask the question, what is the wave function, the spin wave function of the atoms coming out of the oven, the answer is that it doesn't have one. We need to understand this situation. Before proceeding, let me remark that there's a kind of a reverse of this, or converse of this. Here I took an arbitrary two-component spinner, and I found what direction it's pointing in. You can do this in the reverse order, too. Let's say we've got an n hat that's in some given direction, theta and phi. So the usual coordinates, this is sine theta cosine phi for the x, sine theta sine phi for the y component, and cosine theta for the z component. It's a unit vector of spherical coordinates. I guess I'm going to make this a script phi here. Then one can show that if you choose these expansion coefficients alpha and beta to be equal to e to the I phi over 2 times the cosine of theta over 2, and e to the minus I phi over 2 times the sine of theta over 2. And you sandwich this around the three Pauli matrices, you will find that you get this unit vector. So this is just a way of saying that we can find pure state vectors for a spin and half system which point in any direction that we decide. All right. Now, so the question that remains is, how do we describe the quantum state of the beam that emerges from the oven? To answer that, let's think of something of a slightly different experiment. Let's do it this way. In the first place, let's take, instead of measuring the Sx component, let's measure it in some direction n hat. And so, and then pick out the beam which emerges with plus sign. And it is therefore described by a state vector that I'll denote by S n hat plus. It's some normalized vector lying in the eigenspace of the n hat component of spin with an eigenvalue of plus h bar over 2. Let's take this beam and let's feed it into some second measurement of some observable A. We can imagine that there's actually two observers doing this. Let's call them observer number 1 in the first apparatus and observer number 2 in the second apparatus, like this. This observer makes some measurements. Now, to make the game interesting, let's suppose that observer number 1, before passing the beam on to observer number 2, no, let me say that better. Let's suppose that observer number 1, before making a measurement of the spin, suppose observer number 1, when he or she sees an atom coming down the beam, spins a dial and orients this apparatus, the magnet, in a random direction in hat, and then makes the measurement. And if the atom passes on the plus beam, it passes it on to the second observer. So what we might say is the atom which emerges is polarized in a definite direction in hat, but it was one that was randomly chosen by the first observer. Now let's suppose the second observer doesn't have any information about the random direction that the first observer imposed on the beam. All the second observer can do is make measurements of different observables, such as the components of spin. What will the second observer get if he or she measures the average value of all three components of spin? What do you think they're going to get? Well, the answer is 0, because the polarization is in a random direction. The answer is 0 because of the randomness that was introduced by the random direction of polarization. But this is physically equivalent to what you get by measuring the beam coming straight from the oven. And if we're talking about spin, it's a spin Hilbert space, the spin is the only operators there are, then there's no measurement, there is no physical measurement that observer 2 can make that would distinguish between the thermal beam and this beam which is polarized but in a random direction. There's no physical difference between the two. So if we accept the physical equivalence of those two situations, then we can say that the thermal beam achieves the isotropy of the spin not by the choice of the definite state vector, but rather by a random orientation of the state vectors. So this leads us into consideration of statistical ensembles of state vectors. So let me just say a few things about how to set this up. There's two cases to consider, a continuous case and a discrete one. Let's suppose you've got a state vector which is a function of some continuous parameter, lambda, which could stand for more than one parameter. So for example, in this thought experiment up above, lambda could stand for the spherical angles of theta and phi angles of orientation of the first polarization. So lambda is a function of these parameters. And let's suppose these parameters are described by a probability density, which has to be non-negative, and which has to be normalized. So if we integrate f of lambda, we get 1. I'll remind you, lambda here could stand for theta and phi for the direction of n hat above. So this would give us an example of a statistical ensemble of state vectors. Another possibility is we might have a discrete set of state vectors described by a discrete index I instead of a continuous parameter lambda, with corresponding probabilities fi, which are non-negative, and which sum up to 1 because probabilities have to do that. These are two cases, a continuous or a discrete distribution of state vectors. Now, I want to emphasize that these vectors, state vectors that I'm talking about, are not necessarily orthonormal. So, for example, in a discrete case like this, we just have a collection of state vectors with certain probabilities assigned to them. I'm not trying to say that they're orthogonal to one another. To give you an example of that, to go back to the continuous case, in this example up here, this n has pointing one direction, pointing in another direction. Those two state vectors are not orthogonal to each other. There's no requirement that they be. They're just different state vectors that are assigned probabilities. Now, if we have an observable A then, and we wish to compute the average of A as seen by an experimenter, let's work this out in terms of both quantum mechanics and ordinary statistics. In the continuous case, if we knew the state was psi of lambda for a particular value of lambda, the answer would be given by just taking psi of lambda and sandwiching it around sandwiching around A. That's for a known state vector psi lambda. But since we don't know what lambda is, we have to weight this by the probability density in lambda and then integrate over lambda, and that gives us the average value as it would be seen experimentally. Okay. Or in the discrete case, what we get is this. We take psi sub I, sandwich it around A, for a particular state in the ensemble, multiply by the probability, and then sum over the probabilities. So in the discrete and continuous cases, then, this is the result of the measurement of an average value of an operator in these two cases. All right. Now, these two cases can be condensed into a single case by the introduction of the so-called density operator. And the density operator is defined in two ways for the continuous and the discrete case. It's called rho. In the continuous case, it looks like this. It's the integral over the parameters lambda times the probability density in lambda times the outer product of the state psi lambda with itself. Whereas in the discrete case, it's the sum over I of the probabilities Fi times the state psi I outer product with themselves, like this. It's a weighted sum of projection operators, as you see. And the advantage of this notation, so this is the definition of the density operator. The advantage of this notation is that these two expectation values here, in both cases, can be written this way as the trace of rho times A. In fact, I'll write that as the expectation value of A and put a box around it because that's the formula for the expectation value of A. In the general sense, in the general case in which the state of the system is only known in a statistical sense. All right. The reason this works is because of the properties of the trace, which are discussed in this first set of notes that I didn't go over in class. So let me make a few remarks about the trace. As you probably know, the trace of a matrix is a sum of the diagonal matrix elements. This has to be done in an orthonormal basis. So if A is an operator, then the trace of the operator is taken to be the sum on n of the diagonal elements A and n, where n is a discrete basis. And in fact, the answer doesn't depend on which basis you choose. So you can choose any orthonormal basis to do this. The trace has the following properties: is that if you take the trace of the product of two operators, it's the trace in the reverse order. Or if you take the trace of the product of three operators, it's the same as the trace under cyclic permutations, CAB, trace BCA, etc. And trace of a product of any number of operators, the operators can be subjected to a cyclic permutation and the trace doesn't change. These are simple properties of the trace, which I will not prove because you can do them as exercises if you haven't done them before. A similar property is that if you take a trace of an operator which is an outer product, let's say alpha beta, times an ordinary operator A like this, again there's a kind of a cyclic property. You just take this ket alpha on the left and you just cycle it over to the right-hand side and you get the answer. This is equal to beta A alpha, like that. That's the number that comes out by taking the trace. So these are the principal properties of the trace. But then this formula follows because you see, let's take an individual term right here. This term right here, this scalar product, is the same thing as the trace of the projection operator psi I times the operator A. That's what that is. And so pulling out the sum on F and defining rho, you get this expression for the expectation value. Now this is an important formula because this gives this is the general formula in quantum mechanics for computing expectation values. All right. Now, okay, so now I can tell you the difference between a pure and a mixed state. In particular, I can define the pure state that we've been talking about at this point. And a pure state is a state in which the statistical mixture only has one state in it. If I take the discrete case, for example, let's suppose all the probabilities are 0 except for one of them, which is equal to 100%. If that were the case, then the density operator would just be the outer product of the single state that happens to have 100% probability. And in that case, you see the trace of rho times A is just the usual expectation value. This is what you call a pure state. On the other hand, if there are different states which are, have probabilities that are not equal to 100%, probabilities have to add up to 100%, but if they're not just a single probability 100%, then you have a general case which is a mixed state. So mixed state is no Fi is equal to 1 in the discrete case. Actually, I have to qualify this slightly because there's some subtleties about this definition of a pure state. Let me put brackets around this because I want to make a qualification of it. Here's the qualification. Suppose I have a state, let's call it psi naught, and I decide I'm going to give this 50% probability. And let's suppose I have another state which I'll call e to the I alpha psi naught. It's the same state, but it's got a different phase. I'm assuming these states are normalized, by the way. And let's say I assign that also a 50% probability. Is that a mixed state or a pure state? Physically, those two states are the same. It should be a pure state, shouldn't it? Because physically they're the same. Well, notice what happens is if I compute the density operator, it's going to be 1/2 psi 0 coming from the first term, the outer product of this with itself times the probability. And then for the second term, the probability is again 1/2, and I need to take the outer product of this thing with itself. But when I do, the phase factor drops out. And so what you get is just a single psi 0, and in fact it's a pure state. So what I actually said here isn't quite right, because it's not just that no Fi is equal to 1. Really, to say that it's a pure state, it's a mixed state. To say that it's a mixed state means, I'll say it in words and I won't bother to write it out. To say that it's a mixed state means that rho cannot be written in this form. Okay. But this is nice, you see, because this is what you expect. And it tells you the density operator is representing the physics and not some phase conventions. Notice that the phase conventions of the state psi cancel out in the density operator. Okay. The density operator, here's an important point. It contains both a complete and a minimal description of the physics. It contains all the physics and also a minimal description. It contains all the physics because every measurement process that you can carry out can be written in the form of the expectation value of some operator. So if you know the density operator, you know the outcome of all experiments. And it contains a minimal description in the following sense too, is that the density operator has no arbitrary conventions in it, unlike wave functions, which have normalization and all kinds of things involved. Density operators don't. And this is reflected in the fact that it's possible to measure the density operator. That is to say that if I have a system and I make enough measurements on different observables A to get these numbers out, I can use those numbers to determine what the density operator actually is. So the density operator is measurable. And doing it gives you a measure of the statistical state of the statistical quantum state of the ensemble you're dealing with. Here's a question that may have occurred to you. I said a minute ago that if you ask what is the wave function of the spin of the particles coming out of this thermal beam, the answer is it doesn't have a wave function. It has a density operator, which we'll calculate for you maybe next time. If you're dealing with an ordinary accelerator of particles, if you've ever done this and you took a course in quantum mechanics, you surely ask yourself, what is the wave function of the particles coming out? In the courses and in the homework problems, they'll talk about plane waves. That can't be right because plane waves are not normalizable. Sometimes they talk about wave packets and they make them nice Gaussians. Are they Gaussian wave packets coming out of the beam? real beams aren't described, they don't have wave functions, they've got density operators. So the question is actually meaningless. There's some further subtleties of this that I'll tell you about coming up in, well, maybe not the next lecture, but I'll further subtleties about this. All right. What is the density operator, for an example? What is the density operator in this, I've erased it now, in this example of the thermal beam coming out? Well, it's going to be this. It's going to be psi n hat, outer product of psi n hat. These are, let me make a chi just to indicate it's a spinner, polarized in the n hat direction. But then we need to average this over the direction, so I'll call it solid angle v of a will divide by 4 pi. And this will be the density operator. And as far as the chi n hat is concerned, if I say n hat is the same thing as theta and phi to give you the coordinates of it, this is, I explained earlier, as e to the I phi over 2 times cosine theta over 2 times plus e to the minus I phi over 2 sine theta over 2 times minus. And if we do this integral, we get, if we do this outer product here, it's equivalent to, the outer product is equivalent to taking a row vector and multiplying by a column vector. You'll find the matrix in this plus and minus basis looks like this. It's cosine squared theta over 2, sine squared theta over 2. There's an e to the I phi here and an e to the minus I phi here times some other stuff. And when we average over d omega, what happens is that the e to the I phi terms cancel, they go to 0 because e to the I phi averages to 0. Whereas cosine squared and sine squared average to a half. And the result is that the density operator in matrix form is 1/2 in the diagonals and 0 in the off diagonals. Or if you like, it's 1/2 times the identity matrix. And this is the density operator, which is produced by this randomized polarization in this first spin measurement that I was talking about a little while ago. And accepting the physical equivalence of that with the thermal beam, this is also the density operator describing the thermal beam. All right. Now, here's an interesting thing you can do. Let's suppose the first apparatus where the observer measured spin in the n direction and then delivered the plus beam to the second observer. The thermal beam came in. Let's change the game. Instead of polarizing this in a random direction n hat, suppose the first observer just polarizes it randomly between plus and minus z. Just two choices, not a continuous set of choices, but both with 50% probability. So at randomly, half the time it's in a plus z direction and half the time it's in a minus z direction. And what's the density operator in that case? Well, it's equal to 1/2 times the projector in the z plus 1/2 times the projector in the z minus directions, like this. But this is the same thing as 1/2 times the identity operator, because plus minus minus is the resolution of the identity. So it's the same density operator that you get if you randomly polarize in a random direction over the entire sphere. There's two different ensembles, but they give the same density operator. Now, there's an important point in this, which is that the second observer over here can't tell the difference between them. They give the same statistics, so they give the same results in all possible measurements. Now, this is relevant because, if I have time to say it, this is relevant because when you're dealing with a density operator and you're thinking of it as being a weighted sum of pure states, and if you grew up thinking about pure states and wave functions, which we all do, as being somehow God-given in primary, then you're inclined to think of, oh, well, the FIs are just the probabilities. I don't know those because I'm missing some information. But the real states are the psi-i's. That's what you're going to think. And so you're going to, if you see a density operator, you're going to ask, what are the real states, the real wave functions that lie behind the density operator? What this example shows is that there's no answer to that. There's no unique answer to that because a given density operator can be decomposed into pure states and weights in more than one way. So the reality is the density operator. The question about what is the real wave functions, in fact, is meaningless. And this applies also to this question about the wave functions of the particles coming out of an accelerator beam. There really is no meaning to the wave functions of it. Unless you can design the beam so that it produces a pure state, then there are ways of doing that. Well, I better stop. Let me just maybe just mention that this issue of the density operator in quantum mechanics is very similar to subject to polarizations in optics, where you have partial polarizations. And the mathematical formulas is the same. Okay, that's all. But before you go, I want to say that would you please prepare to have a makeup lecture next Tuesday night, 7 to 8 p.m. I'll make an announcement by email what the room will be. This will give us 3 lectures next week because we're not meeting on Monday, so it's no worse than a regular week. And it'll give me ahead of the game when I have to leave town, which is coming up pretty soon. I'll send out an email. The notes don't always follow the lectures, but at the beginning, of course, they're pretty close later on in the night. I'm probably going to lecture on some variations in the course, so later on there's some things that are different. Okay, the last time at the end of the hour, we were in the process of examining this question about the possibility of degeneracies. I'll remind you that in the Stern-Gerlach experiments, there was no evidence on the basis of measurements of spin that the Hilbert space had any more than 2 dimensions. And so we just assumed, for the sake of simplicity, that it had exactly 2 dimensions, so that each of the eigenspaces of the various components of magnetic moment were one-dimensional. Now the question is that, and I promised we'd come back and examine the question of degeneracies later. So that's what we're doing now. The question we want to ask is that if there were degeneracies, how would we know? This is not a mathematical question, it's one of physics. It has to start from the postulates of quantum mechanics. So to answer this question, I'd like to examine a somewhat idealized experimental situation in which we imagine that we've got some pure state, initial pure state psi 0. We make a measurement of an observable A, and we throw away all the outcomes except A sub n. Then, according to the postulates of quantum mechanics, after this measurement, the state of the system, which I'm calling psi 1, is given by the projection operator, which projects onto the nth eigenstate of the observable A. That's what I mean by PAN. Acting on psi 0 gives me the new state psi 1. We then take this psi 1 state and we feed it into a second measurement of a different observable B, which also has a bunch of outcomes, but we throw them all away except for one of them we call B sub m. And again, according to the postulates of quantum mechanics, the state that emerges after the measurement of B sub m with the eigenvalue Lorca. After the measurement of B with the eigenvalue B sub m was given by the projection operator onto the eigenspace of the operator B with eigenvalue Bm acting on psi 1. That's the state psi 2. Okay, that's just following the postulates. Now, let's ask for the probability that we measure first AN and then secondly B sub m in a sequence of experiments, a sequence of measurements like this. This is a product probability. First, we need to multiply the probability of measuring AN in the first place by the postulates of quantum mechanics, that's given by taking the input state psi 0 here and sandwiching it around the projection operator PAN. And then dividing by the norm of psi 0, square norm of psi 0. That's the probability of getting the AN. And then we need to multiply by the conditional probability of getting B sub m, given that we had AN in the first place. And that probability is again by the postulates of quantum mechanics, given by taking the input state psi 1, sandwiching it around this projection operator P sub Bm, and circumstances in which these two probabilities are equal. They're equal in particular if the operators, A and B, the two observables, commute with one another. This is because if the observables commute, it implies that their projection operators commute. PAN and PDM commute. This follows because projection operators are actually functions of the original operators themselves, and functions of commuting operators are commuting. So in the present case, it means, for example, in this enumerator up above, I can take the PDM and move it to the right of the PA, we're pumping in the PAN squared, and that's just PA because it's idempotent. So you get the product PAN times PBM in the upper expression. Likewise, in the lower expression, I can take this PBM and move it to the right of the PA, and then you get a PB squared, which is the same as the without the square. So again, you get the same product here. You can write this in either order, of course, because they commute. But the point is that the two expressions now become equal. So we can say that these probabilities are equal if the operators commute, A and B. And this is a consequence, as I just explained, of the measurement postulates of quantum mechanics. All right. Now, there's a converse of this as well. Oh, by the way, the mu x and mu z, for example, in the Stern-Gerlach experiments, certainly don't commute, and so these probabilities are not equal for that kind of experiment. But they do commute when we have equal probabilities. Now, there's a converse of this as well, which is that if the that's what we get. All right. Now, suppose we perform the experiments in the reverse order, doing the A first, the B first, and measuring B sub m, and then A second, and measuring A sub n. And let's write down what the probability is for doing that in a reverse order. The formula is just the same as the one above, except we swap the A's and the B's and the N's and the M's. So it's psi 0, P B M, P A N, P B sub m, psi 0 divided by norm squared psi 0, like this. Now the question is, are these probabilities equal? Do we get the same answer? And the answer is no, because in general these projection operators, the A and the B projection operators, don't commute with one another. So the triple product in the first expression and the one in the second expression are the same. This is something that is one of the surprising aspects of quantum mechanics. In a sense, it's a saying that the measurement of one of these observables mixes up the statistics of the other one. We saw this already in measurements of magnetic moment. If we measure the mu x first, it affects the outcome of the subsequent mu z measurement. It changes the statistics of the mu z's. Likewise here, doing this in one order or the other makes a difference because measuring one observable affects the statistical outcome of the measurement of the second observable. Now, on the other hand, there are divided by the norm of psi 1. So this is the compound probability. Now, let's take this denominator psi 1 here, and let's plug in this expression for psi 1 in terms of this projector. Gives us, in terms of PA0, PAN acting on psi 0. If I take this as a bra, I turn it around and I get a PAN dagger. So this is the same thing as psi 0, P sub AN dagger times P sub AN times psi 0. That's that denominator. However, projection operators have emission, so I can drop the dagger if I want the left-hand factor. And projection operators are idempotent too. That means their square is equal to the operator itself. So we get the square of PAN in here, but it can just be replaced by a single copy of PAN, like that. And if we do this, and we see that this denominator, psi 1 cancels with the numerator up above. Now likewise, this numerator that has psi 1's in here, we can substitute in and express it in terms of psi 0s using, again, this expression. And so if I copy this down, I get to clean it up and copy it down, I get the probability of these two successive measurements giving two given successive outcomes as being equal to the state psi 0 sandwiched around a product of three projection operators, PBM, it's PAN, PBM, PAN, psi 0, divided by the square norm psi 0, the normalization.